In previous videos, we've been focusing on dehydrohalogenation by the E2 mechanism. In this video, we're going to look briefly at other mechanisms of dehydrohalogenation, and we're going to look at an example of elimination in a biological system. And then in the next videos, we're going to come back and look again at dehydrohalogenation by E2 in competition with substitution reactions. Keep in mind, when we talked about dehydration reactions, if we have an alcohol and we treat it with a strong acid and we heat up the reaction, we can lose water to form an alkene. The mechanism depends on the structure of the alcohol. So for a primary alcohol, this will go through the E2 mechanism. Secondary or tertiary alcohols, this will go through the E1 mechanism, which proceeds through a carbocation. For a primary alcohol, E2, no carbocation. So for dehydration, the mechanism depends on the structure of the alcohol. In contrast, for dehydrohalogenation reactions, if we have an alkyl halide and it's treated with a strong base such as an alkoxide, once again, remember, we're talking about methoxide with the sodium counterion in methanol. Methoxide is a stronger base, so methanol is just the solvent. So strong base such as an alkoxide base and an alkyl halide, this is going to give us elimination by the E2 mechanism. The E2 mechanism works for a tertiary or a secondary or a primary alkyl halide. Unlike what we saw with dehydration, where the mechanism depends on the structure of the alcohol, with dehydrohalogenation, the E2 mechanism can occur with any structure of alkyl halide as long as we're using a strong base. But there are other pathways or other mechanisms by which dehydrohalogenation can occur as well. If we have a tertiary alkyl halide and we do not treat it with a strong base, we just have a mild base such as water, we can get some elimination product. For this reaction, the rate law says that the rate is equal to a rate constant K times the concentration of the alkyl halide. So the nucleophile, or the base, does not appear in the rate law. So what this should tell you is that this mechanism proceeds through a carbocation. So chlorine can leave and we form our carbocation. And then water can act as a base and grab off one of these protons. These electrons can fold in here to form a double bond. Giving us an alkene product by the E1 mechanism. Elimination, unimolecular, because carbocation formation is the rate determining step, and there's only one molecule involved in the transition state of the rate determining step. But there are some problems with the E1 mechanism. So first of all, because it goes through a carbocation, there is the possibility of carbocation rearrangement. And another issue, if you recall, we saw this in earlier chapters talking about substitution. So when we have an alkyl halide, especially a tertiary alkyl halide, and we react it with a very, very weak base such as water, what we're actually going to get is a mixture of elimination and substitution. Because after carbocation formation, water can act as a base or it can act as a nucleophile. So if it acts as a base, it leads to the elimination product. If it acts as a nucleophile, that leads to the substitution product. So there's going to be a difference if you're trying to get more of the substitution versus if you're trying to get more of the elimination. You can try to play around with the temperature, but in general, we're going to get a mixture. So if you are trying to get substitution, then Great. You treat your alkyl halide with water and figure out how to maximize your substitution and minimize your elimination. If your goal is to do an elimination, well, why not do it by E2 elimination? Because then you don't have to worry about substitution for this type of reaction. There are some potential advantages to E1 mechanism. We don't have the stereoelectronic requirement that we saw in the E2 reaction, so in some cases that might be to our advantage. But in general, E1 elimination is more limited, so I'm never going to expect that. I'm going to focus on E2 elimination in general. A different elimination mechanism is called E1CB, elimination unimolecular by the conjugate base. So for example, if we have an alkyl halide, or whatever our leaving group is, then a base would abstract a proton from the carbon adjacent to the leaving group, and then these electrons would sit on the carbon, giving us this conjugate base. And now these electrons can fold in here to form the double bond, pushing away the leaving group, giving us this alkene. Now, this does not happen with a regular alkyl halide. It requires something very specific about this molecule to make this proton somewhat acidic. So for example, if we have a carbonyl, hydrogens on a carbon connected to a carbonyl are much more acidic than regular hydrogens on sp3 hybridized carbons. So here it is possible for a base, I'm not getting into specifics, a base can grab off this proton and we get as an intermediate this conjugate base. This is stabilized by resonance. So this conjugate base is stabilized by resonance, which is what makes this hydrogen a little bit more acidic than a typical hydrogen on an sp3 hybridized carbon. And then from here, we could either picture it happening from here where these electrons fold in here, pushing away the leaving group, or if we filled in the details of our lone pairs here, then we could imagine these electrons fold in, these electrons flip over here, pushing away the leaving group, leading to this product. Oops, that's a CH2. For the simple molecules that we usually talk about, the E1CB mechanism is not very common. So this was mostly just for your information. It's not something that we're going to be using. So I just wanted you to be aware that there are other dehydrohalogenation mechanisms that could occur, but we will still focus on E2 elimination. Here is a quick peek at an example of a biological elimination reaction. And this is involved in the biosynthesis of fats and oils. And here we have a thioester, so the carbonyl connected to a sulfur connected to some R group. And then here we have the adjacent carbon with the adjacent hydrogens. And then on the next carbon, we have a leaving group. In the organic lab, this would be a really bad leaving group, but because this is happening at an enzyme active site, different amino acid residues can make this a more reasonable reaction. So we could have a histidine residue, so an amino acid acts as a base, grabs off a proton, forming the conjugate base that looks like this, and then these electrons can come back in here, push these over here, pushing away the leaving group as it grabs a proton. This is not going to happen where the OH jumps off and grabs a proton in the organic lab. It's not a typical process for how electrons are moving around, except in an enzyme active site. But the overall result is that we have lost water and we formed a new alkene. And so this would be actually a dehydration by the E1CB mechanism.